Hi, this is Mrs. Evans, and we're going to do a short lesson on how to remove a discontinuity. The first thing that you need to know is that all polynomial functions are continuous. So you're not going to have to worry about removing discontinuities when you're talking about polynomial functions. Most of the time, when we have to remove a discontinuity, we are talking about rational functions and piecewise functions. And so we're going to show a few examples of those for you today. When you remove a discontinuity, the only kind you can remove are the removable discontinuities. A non-removable discontinuity has a vertical asymptote or a jump step discontinuity to it, and those we can't remove. So we're really going to be talking about removing removable discontinuities, and those are when you have holes in the graph. So this lesson hopefully will let you connect the graph with the algebra behind it. So go grab your graphing calculator and let's get started. First thing that we need to look at is that you could possibly have discontinuities when you have rational functions. F of x is a rational function. The two types of discontinuities that you will run into with this type of function is a hole, which is removable, or an asymptote, which is non-removable. You don't have to worry about the step or jump ones in this case because that is usually when you are working with a piecewise function. So we're going to start with this one right here. And what you need to know about this one is to figure out where your discontinuities are possibly, you have to think about what makes the denominator equal to 0. So look at that denominator right there. It's the difference of two perfect squares. So to figure out where you could possibly have discontinuities, you want to figure out where this equals 0. Personally, I like to factor. So I went ahead and factored this for you, and I factored the bottom into x minus 2 times x plus 2. So I have two possible discontinuities. I have a possible discontinuity at x equals 2 and one at x equals negative 2. Whether or not they're a hole or an asymptote is what I have to find out. So I'm going to go ahead and graph it using my TI calculator, and if you want to go ahead and do that with me, go ahead. So grab your graphing calculator and go to the y equals screen. So to get to your y equals screen, you go from your home page. If you are not someone who understands this very well, here's your home page or your home screen, and you want to go to this y equals button here. And in that, I want to graph this function. So I have to put parentheses x squared minus 3x minus 10. I have to end my parentheses, put a divided by symbol. I have to add another parentheses and go x squared minus 4. Now the reason for the parentheses is you always do division before addition and subtraction. So if I didn't have my parentheses, the calculator would think that I wanted to do a division of negative 10 divided by x squared in the middle, when really I want to take this whole function divided by this entire function. That's why I need a parentheses. Now most of the time people will go to zoom 6. Zoom 6 is a standard window. It goes from negative 10 to positive 10 in the x and in the y direction. Cool part about this is it usually shows the majority of the graph that you need to see. But the negative part about it is it actually skews your picture a little bit and makes it like if you were graphing a circle, it would make it look like an ellipse instead of a circle. So zoom 6 is a nice window to have, but sometimes you want to look at a little more square. So you might want to go to zoom 4 instead. Zoom 4 is a decimal window, and if we go to a decimal window, it'll square up your window a lot more and you'll be able to see things a little bit better. If you'll notice, it looks as if we have a vertical asymptote right here. And I'm going to go back to zoom 6 real quick, and the calculator is connecting it in this window with that line, and it looks like that there is an asymptote at x equals positive 2. But over at x equals negative 2, when I look over here, I kind of see a little bit of a gap in the graph, or possibly a hole. So right now I have a guess. My guess is that I'm going to have a vertical asymptote at x equals positive 2 and a hole at x equals negative 2. Well, let's see what that looks like graphically. If I look at this graphically, I have to factor the top also. And when I factor the top, I get x minus 5 times x plus 2 over x minus 2 times x plus 2. And what you'll notice is this. What's kind of cool about this is I actually can mark out my x plus 2's. When I mark out my x plus 2's, I no longer have a discontinuity there. I have just gotten rid of the discontinuity. So here was the picture I had before, and right here was my hole in the graph, right there. Well, if I take negative 2 out of the picture, then I no longer have a discontinuity there, and I'll have a graph that looks just like it. But if you'll notice, I can't get rid of x minus 2. X minus 2 means I have a vertical asymptote at x equals positive 2. It's because what makes this 0. What makes that 0 is a positive 2. So let me show you really quickly on the graphing calculator. So right here I have a hole, and what I'm going to do is I'm going to go back to y equals, and in my y2 I am actually going to graph this second function, the one that has the x plus 2's marked out, and I'm going to go x minus 5, x minus 5, parenthesis, divided by x minus 2. X minus 2, parenthesis, and I'm going to graph that. And what I'm going to do when I graph this is I'm going to make the graph a little bit different so I can see the difference between the two of them. I'll make that one a thicker line. So watch what happens. I'm going to hit graph, and if you'll notice, it's the exact same graph. It had the lighter one underneath at first, and now it has the darker one over the top of it. The difference is that there's no hole right there. So actually, these two functions are not the same. My first function, which I have here down on the bottom, actually had a hole and a vertical asymptote. This function looks identical with the exception that I no longer have a hole. So these two functions look a lot alike graphically, but they are not identical, so you have to be really careful. Now let me show you how you remove it utilizing what we call a piecewise function. So here we have another rational function, and this rational function looks like I only have one potential of discontinuity in the bottom. X equals 10 is my discontinuity. Whether it's a hole or a vertical asymptote is something I have to figure out. I could spend some time graphing this, or I could just take care of it algebraically. And the way to take care of it algebraically is to actually factor the top also. So I'm going to go ahead and factor the top, and when I factored the top I got x minus 10 times x minus 10. And what I noticed was that I could actually mark out one set of x minus 10's. And what that means is that the original function, that big graph, looks exactly like the graph of y equals x minus 10, which is just a line, but the difference is there was a hole at x equals 10. I know there's a hole because I was able to remove it algebraically. So that meant that there wasn't an asymptote there. Now, to make it have a hole filled, to actually plug the hole, you have to write it as a piecewise function. So here's your piecewise function. And what I did with the piecewise function is I wrote the original equation first, and I said, but the problem is x cannot equal 10, because if x equals 10, the function is not defined. Then I said, I'm going to plug the hole by putting in a 0 when x actually equals 10. But I didn't just come up with 0, and it's not always going to be 0 for your answer. What I actually did is I came up here, and I knew 10 was the issue. So I wanted to get really, really, really close to 10 to figure out what was going on. So I took a limit of this function right here. The limit as x approaches 10 of x minus 10, I plug in a 10 and I get 10 minus 10 is 0. So when x equals 10, 0 is my answer, and therefore now it is a continuous function and it no longer has a hole at x equals 10. So that's how you remove a hole or a removable discontinuity. See you soon.